Can a person become a black hole? Yes, under the circumstances that all of your matter, all the atoms that make up your body, got compressed into a space of approximately 10 to the minus 23 centimeters, which is much smaller than the nucleus of an atom, by the way. Under those circumstances, you would be within the Schwarzschild radius of your mass, and your body would undergo irreversible gravitational collapse, and you would become a black hole. Now, you would be a much less massive black hole than the black holes that originate from stars, or certainly smaller than the mass of the black hole at the center of our galaxy. However, it is possible if you underwent that kind of pressure and force, and you were compressed into that small of a volume. Who discovered black holes? Subrahmanyan Chandrasekhar did, because although the mathematical solutions to the Einstein field equations admitted singularities, they were believed to be purely mathematical and not physical. Subrahmanyan Chandrasekhar came along and he actually did calculations using quantum mechanics as well as general relativity to devise his Chandrasekhar limit, showing that black holes could actually exist and come from collapsed stars. In addition to traditional photons, the sun also produces tons of radiation in the form of charged particles. Typically, they're electrons and protons, and it's called the solar wind. Basically, what happens is these particles get trapped in the magnetic fields generated by the sun, and it works like a supergiant particle accelerator, where these particles just get accelerated faster and faster, and they reach enormous temperatures because they heat up the surrounding atmosphere of the sun. But what happens is the magnetic field lines produced in these areas get crossed sometimes, and it spits out a huge number of these particles called coronal mass ejections. When these come towards Earth, it's a good thing that we have a magnetic field, because the magnetic field takes those charged particles and redirects them to the North Pole, where it interacts with atmospheric gas, creating the northern lights. What is the Schwarzschild radius? Well, as you can see, it's 2gm over c squared. 2 is just a constant. G is also a constant, Newton's gravitational constant. And m is a variable. It's the mass of the object in question. Then all of that divided by c squared. C is also a constant. Now, since it's the speed of light. Now, since big M is variable, it means the more massive the object is, the larger the Schwarzschild radius, since it's in the numerator. So that means that the more massive a black hole is, the larger its event horizon is and the harder it is to escape from. This term came about when Carl Schwarzschild solved the Einstein field equations for a central potential, meaning like a compact object with most of its mass at the center. If you fall into a black hole and die, could you someday be reborn? Yes, as Hawking radiation. So it turns out that along the perimeter of the event horizon, which is the area that you can't escape from if you go inside of that for a black hole, just on the boundary, there's quantum fluctuations in the vacuum where there's particles of matter and antimatter continuously popping into existence and then recombining and annihilating back into a quantum field. But if it happens at the boundary of an event horizon, one of those particles, either the electron or the positron, could get pulled in and the other one escapes and doesn't annihilate. But it takes energy for that particle to go off, and it has to come from the black hole. So the mass of the black hole evaporates and is Hawking radiation, and your body that's trapped inside the black hole could become that radiation. What is a white hole? When we solve the Einstein field equations and we put in a spherical potential, we get 3 types of solutions that have singularities: a black hole, a white hole, and a wormhole. For a white hole, it's the case that you cannot enter this region and everything escapes. Nothing can stay in that spot. It's very much the opposite of a black hole. The interesting thing is that while none have been observed directly, we have no way of really knowing if they exist or not, and they might be found in some other physical process. For example, when matter and antimatter meet, they annihilate into pure energy, and they do not stay in that region. Maybe it's a miniature white hole that's created for annihilation of particles. So what is a vacuum? The vacuum is all the empty space that doesn't have any gas or stars or planets or anything else in it. But it turns out that this space isn't empty. So first of all, on average, there's 1 to 3 hydrogen atoms per cubic meter. Now that isn't a lot of mass, so that is very empty. But it turns out there's a lot more. There's all this vacuum energy. There's these quantum fields that have existed since the time of the Big Bang. And what happened was the Big Bang caused the universe to expand, and the fields just came right along for the ride. So everywhere you go in this vacuum, there's these quantum fields, and they can do some really crazy things. For example, they can violate energy conservation by creating particles as long as the matter and the antimatter annihilate in a short enough time. And they can do a lot of other things too, which I'll talk about in some more videos coming up. Can you touch plutonium and live? If you research plutonium, you'll see 2 conflicting accounts. On the one hand, you'll read that plutonium is dangerous, but it's a heavy metal like anything else, and it's not really that much more toxic than lead. But you'll also see 2 stories about 2 separate incidences at Los Alamos National Laboratory where 2 men lost their lives experimenting with plutonium about the size of my fist. So which one is it? Well, it depends on whether or not the plutonium is subcritical or not. If it's subcritical, meaning that it can't undergo sustained nuclear chain reactions, then it's probably safe to be in the same room with it, and you shouldn't touch it, but a little bit of shielding is all you need to protect yourself. However, if it's critical, not only can you not touch it, but you cannot be in the same room with it even. If you are, you will definitely die, and it only takes seconds to get the exposure. What is the Higgs boson? Well, it turns out that in every region of space and time, we believe there's a field called the Higgs field. It's a quantum field, and it interacts with particles like electrons to give them mass. Now, if you actually create enough energy in the right way in some region of space and time, and it can be any region, you can actually create a Higgs boson that you can detect. But you have to have tremendous amounts of energy. So what they can do is they take protons and they collide them so that one proton going this way, another going this way. They smash into each other. And if they can do it with enough energy, this Higgs boson pops into existence for a very short amount of time. So short, in fact, that we still can't detect it directly. But it decays into particles that we think can only indicate that it was there. Wormholes and quantum entangled systems might be the same thing. Let's see about this. So, we know that a wormhole is 2 distantly connected regions of space-time. It could be on other sides of the galaxy, and if we travel through, we can get from one side to the other. Basically, think of it as 2 black holes that are somehow connected. And we know that an entangled system is when we do something to one part of the quantum system, it can affect the other side, also across any distance, even on the other side of the universe. What if we take a huge collection of particles and we entangle them with another system of entangled particles? And then we add so many particles mathematically that we collapse both systems to black holes. They're still entangled and they're now a wormhole. This is the connection. This was a huge revelation in physics, and it's very modern. It was discovered in 2013. If I'm at sea level, is the passage of time different than if I'm on Mount Everest? Yes. It turns out that gravitational fields strongly affect the passage of time, something that was discovered with Albert Einstein's theory of general relativity. It turns out that the gravitational field is stronger at sea level than it is on Mount Everest. And the stronger the gravitational field is, the slower time passes. So time passes more quickly on Mount Everest. If we're going into space and we travel to an area that has a really strong gravitational field, like say near the galactic center, near a supermassive black hole, the effect is even more pronounced and time will really go slower than if we were, say, near something where there isn't very much of a gravitational field. At a temperature of 464 degrees Celsius, Venus is the hottest planet in the solar system, but it's not the closest to the sun. You would think that Mercury, being the closest, would be the hottest since it gets the most intense flux of solar radiation. But actually, it has very little atmosphere, so there's no way for heat to get trapped. Meanwhile, Venus has tons of greenhouse gases of CO2. It has an extremely thick atmosphere, which means that it's very good at trapping heat and warming it. So yes, Venus is one of the strongest pieces of evidence that we have that CO2 does contribute to global temperatures being much higher, because Venus is not the closest to the sun, yet it is far hotter than another planet that gets way more radiation. But the difference is that it has an atmosphere of greenhouse gases. To understand global warming, you really need to understand quantum mechanics. It turns out that CO2 and all other molecules can only absorb light of certain frequencies. They have energy levels, which means that they can only take in energies at certain wavelengths of light. It turns out that CO2 really likes the heat frequencies. And what happens is the light will come up and it will change the energy level of the CO2 by the CO2 absorbing it. Then the CO2 will do another thing. It will re-emit the light in some random direction. The fact that it's random is also a quantum mechanical effect. But what that means is there's a 50% chance that the CO2 will just re-radiate the light back down to the surface of the Earth instead of out into space. So there's this endless cycle of heat coming up, getting absorbed by the CO2, and then being re-radiated back downwards. When James Clerk Maxwell discovered that light was a wave with an oscillating and electric and magnetic field going through space, many scientists, including himself, believed that there must be an ether that it was traveling through. But Albert Einstein later showed that it does not need an ether to propagate. So if light is a wave, the same kind of mathematical wave as a water wave, why does it not need a water to travel through? Well, it turns out that what light is actually is a wave, but it's an excitation of a quantum field. And since that quantum field is throughout all of space, the electromagnetic field, the excitation is what travels. And we call that excitation a photon. Venus is definitely one of the craziest planets in our solar system. Not only is it extremely hot, which makes it extremely inhospitable to life, but it turns out it has another amazing property that also makes it inhospitable. It has an extremely dense atmosphere, and the air consisting of its atmosphere is mostly carbon dioxide, but it's so thick that if you were just standing on the surface of Venus, there would be the same amount of pressure on you, on your body, as if you were 3,000 feet below the surface of the ocean. Amazing. You would be absolutely crushed by the pressure of the atmosphere on the surface of Venus. Amazing. Can you stick your head inside a particle accelerator and live? Yes. In 1978, Anatoly Bogorsky was checking a malfunctioning piece of equipment. He was basically leaning over through the path of where the protons would go in, checking to see what was wrong. And as he's checking, the machine switches on unexpectedly, and a 76 giga, that's billion electron volt proton beam went through one side of his back of his head, out through the front. He was so horrified because he saw a flash like a million suns, but he didn't even tell anybody that he worked with there because he thought he was going to die anyway. What was the point of telling someone? But amazingly, he didn't die. Although his face swelled up and he occasionally suffered seizures, he survived and was even able to complete his PhD. Thanks for watching, and if you like this video, hit the like button. In the film Doctor Strange 2, they travel across an infinite number of universes using their special powers and accessing portals. The question is it possible that we live in a universe where there's actually an infinite number of universes? Yes, it turns out that this is possible. You see, there's nothing special about our point in space-time where the Big Bang occurred. At that point, there could be an infinite number of neighboring points that are just as valid a starting point as ours. And when our Big Bang started, it is possible that an infinite number of other Big Bangs started, creating an infinite universe of infinite universes. Amazing. Now, are those accessible to us? That's a question for my next video. So this is a follow-up to my first video on Doctor Strange 2, where I answered the question, would it actually be possible to travel to multiple universes if they existed? According to the laws of general relativity, no, it wouldn't be possible. However, quantum mechanics has something else to say about it. Let's start with general relativity. In general relativity, when the Big Bang happens, there's a light cone created. It's basically the speed of light traces out a path and it looks like a cone in every direction. You cannot travel outside of this cone, so traveling to another universe would mean violating causality and going faster than the speed of light. However, in quantum mechanics, there's a theory called many worlds, where the quantum wave function, when it never collapses, but when it interacts with something, it splits off and every possible outcome occurs. So quantum mechanics leaves the question open. How does a black hole kill you? Well, if you're falling in from outside the black hole, it's fairly obvious that the rapid acceleration is going to basically burn you up. But here's a more interesting way to die from a black hole. Let's say right here on Earth, we're suddenly surrounded by a miniature black hole. How do we die then? Well, the black hole has so much force that it overcomes degeneracy pressure. That's the pressure determining the size of our atoms. Basically, it prevents more than one particle from occupying a certain quantum state if it's a fermion. Electrons and protons are just that. So as long as we have this degeneracy pressure, we're in good shape. We have a certain amount of volume and that volume stays fixed. But the black hole will squish us. It'll basically take all that empty space and compress it so we're at a point. How did the Big Bang even happen in the first place? There's an equation called the Ricci flow equation. And what it is it's an equation that basically starts out as a singularity and it explodes outwards. Now, there's a lot of different ways that this can go, but basically it's a type of curvature flow where it tries to straighten itself out over time. Sound familiar? Kind of like the Big Bang, right? We start off with an infinitely curved region of space-time, then an explosion, and then the universe seems to be getting flatter and flatter. At least it appears so for right now for observations. But the interesting thing is, where does this energy even come from? Well, if we compressed all that energy into a tiny space, just like we took a spring and we compress it into a smaller and smaller region, the energy could be there by virtue of just being confined to that singular point. Can you hang out on the perimeter of an atomic bomb explosion or walk through ground zero just a few hours after the explosion has gone off and live? Yes. At the end of World War II and right after during the Cold War, hundreds of thousands of U.S. soldiers were exposed to these explosions. They would bring these soldiers out to the middle of the desert, usually someplace out near Nevada, and they would set off these explosions. They would have the soldiers cover their eyes or look away, and they would wear a minimum of protective gear, sometimes just a helmet and maybe a gas mask. They didn't know how dangerous the radiation was back then, but these soldiers were in some cases exposed to the lifetime dose of radiation that's safe. And in some cases, it was as if they'd smoked 3 packs of cigarettes a day for their whole lives and had the same cancer risk as that. There's a landfill in the United States with a terrible secret. During World War II, Mallinckrodt Chemical Company was in charge of enriching the uranium that would later be used in the atomic bombs. Now, a lot of people know about New Mexico as the test locations for these atomic bombs in Nevada, but actually, this enrichment was done in none other than St. Louis, Missouri. Now, this is kind of scary because St. Louis is a very populated region. Well, just as you can imagine, there was a lot of nuclear waste, and it was buried in this landfill. It was originally called Westlake, but now it usually goes by a different name. They keep changing the name because it's continually putting out radiation, it leaks into the groundwater, and sometimes the landfill even spontaneously catches fire. This is the Schrodinger equation. Okay, but what does it mean? Well, the first term is just the kinetic energy of the system, minus h bar squared over 2m d2 psi by dx squared. It's the same thing as 1/2 mv squared, or p squared over 2m. The next term is just the potential energy of the system. Okay, but there's one big difference. It turns out that in order to get the energy of the system, you have to operate on the wave function. So d2 psi by dx squared is an operator that operates on psi to give you the kinetic energy, and v also operates on psi to give you the potential energy. You've probably heard about the wave function if you've heard about quantum mechanics, and how it can describe a particle with mass like an electron that has both a wave-like property and a particle-like property simultaneously. But how can this make sense? Well, we have to think about it as if the electron is a field, because it turns out that the electron is an excitation of the electromagnetic field. So when it encounters two different locations, like two holes in a screen, it can actually go through both at the same time. And we can't treat it as having any definite location unless we measure it. But what does it mean to be measured? Well, more and more, it's looking like this measurement is an interaction. So essentially, the electron travels through both holes like a field, but then if it's forced to interact, it localizes and it shows itself as a particle. Every 300,000 or so years on average, Earth's magnetic fields do something crazy. They change polarity, meaning what was once the north magnetic pole becomes the south magnetic pole, and vice versa. But why does this happen? Well, it turns out that Earth's magnetic field is caused by its iron core, and this core is rotating. Now, the process by which the magnetic field is generated essentially involves rotations of magnetic moments. And what happens is there's a magnetic field that is continually created, but it's also continually varying, meaning at any given instant, the magnetic poles are always shifting. But incredibly, over time, these shifts can cause balances to go off, and we can completely shift polarity. In the late 1960s, astronomers started observing these strange, pulsing patterns of light. They termed them pulsars. Jocelyn Bell made the initial discovery that ultimately pointed to them being neutron stars. What it is a neutron star will be rotating rapidly. So the strange state of matter that it's in, where it's all neutrons, means that it can rotate, and it can actually rotate extremely rapidly. When it rotates, this magnetized field is created, and it emits a type of radiation from its poles, north and south. But since it's rotating, we can only see this light being emitted from its poles when it rotates and points directly at us. Hence, it looks like a pulsing pattern of light. And this light is extremely high frequency. We're talking about gamma rays. Why is the sky blue? Well, it's because of the nitrogen and oxygen atoms that make up the majority of our atmosphere. They scatter light in that range more efficiently. And in order for you to see something, it has to be scattered, because if it's scattered, then it can finally make its way into your eye, where the cell receptors, the photoreceptors that is, will register the color. So the color of an object is the light that scatters off of it. The absorbed frequencies you don't see, they never make it to your eye. Okay, but what's special about this blue frequency range? Well, there's something called Rayleigh scattering, and basically the light bounces off of these atoms elastically, and it bounces very efficiently in the blue range. In fact, it's inversely proportional to the wavelength to the fourth power, so shorter wavelengths scatter most efficiently. The neutron bomb is simply one of the strangest, most devastating weapons ever conceived of by humanity. You see, it doesn't kill you with the blast or a shock wave the way a traditional bomb does. It kills you with neutrons, these subatomic particles that are the components of atomic nuclei. You see, when the reaction happens, these neutrons normally are created and they're absorbed into creating more explosions. But with the neutron bomb, they allow these neutrons to escape into the underlying environment, and they penetrate buildings. They go right through any kinds of structures and kill all the people inside. These neutron bombs are therefore extremely dangerous because they can actively kill a whole population, and then the city is still livable afterwards because neutrons decay after about 8 minutes. I currently research dark matter using large-scale galaxy simulations, and specifically I'm studying the effects that would occur if dark matter is its own antiparticle and it annihilates in areas where there's a high density of dark matter and produces a signal. For example, we observe gamma ray photons in the galactic center of the Milky Way and Andromeda, and we're trying to figure out the source of these. It could be that dark matter is interacting with itself, creating these annihilation events, and that could be the source of the gamma rays. However, it could also be due to millisecond pulsars or heated gas. However, depending upon whether it's any one of these three sources, there should be a specific characteristic shape associated with these different interaction events. So characterizing the shape is a very important goal in the future for ruling out whether or not dark matter could be behind these processes. If the Earth suddenly became transparent, yet pressureless, what would happen? Well, you would immediately start falling through down to the center because most of the mass would be away from you, so it would be pulling you downwards. Once you reached the center of the Earth, you would be going a maximum velocity, but you wouldn't stop even though the force would be equal on all sides because you'd be going too fast to stop. So you would go right through, but then as you cross through the center of the Earth, you would slow down because there would be more mass pulling away from you on the other side. So you would decelerate all the way to the other side where you would finally come to a stop, and then you would free fall all the way back again like a spring going back and forth, back and forth. And what's crazy is this kind of free fall is actually a type of orbit. When you're in the space station in orbit around the Earth, is there gravity? Why are you floating? Well, there is gravity, and we know there has to be because if there was no gravity, the Earth would simply zoom away from us and we would be left all alone in outer space because the Earth is going hundreds of thousands of miles per hour. But then why isn't it like when we're on Earth on the ground? Well, when you're orbiting an object like the Earth, you're actually falling, but you're falling in such a way that you never hit the ground. You just go around and you keep free falling forever. Remember when I talked about in my other video, if the Earth was transparent, you would do a kind of orbit where you just free fall continually? Well, yeah, an orbit is another kind of those, the traditional one. Runaway stars are created when you have a collection of stars orbiting in a chaotic orbit. This can happen if you have a large collection of stars of similar masses in something like a globular cluster. Here I have a simulation of stars in an orbit from a Barnes Hut simulation, and you can see that occasionally a star will go off the screen. These point masses represent a collection of 100 stars, to be precise. So when the orbits get very chaotic, they can happen where a star actually gets pushed out far enough that it doesn't come back to orbit the common center of mass, which is represented by the blue check that you can see right there. Every year in its journey around the sun, the Earth travels 149.60 million kilometers or 92.96 million miles. That means that at this very moment, you're traveling 67,000 miles per hour. But wait, how is that possible? How come we're not breaking the sound barrier? Well, Earth is traveling through interstellar space, and there's really no gas out there for which to break a sound barrier through. You have to be traveling in a fluid to break a sound barrier. and all the gas is gravitationally bound to the Earth, so relative to us, it's not moving any faster than we are. Now, how come we can't detect this rapid velocity? Because our brains have not evolved to detect constant velocity. We can only detect accelerations. When you're at the equator, do you move faster than if you're at the North or South Pole or anywhere in between? Yes. That's because the Earth is always spinning about a constant axis. And that axis is such that when you're on the equator, you go about 1,000 miles per hour as part of this spin. Whereas if you're on either pole, you're not really covering any distance, so you have no velocity in terms of the spin. Now, everybody on Earth, regardless of where you are, has a velocity from going around the sun, but that's regular angular momentum. With the Earth spinning, and it spins 24,000 miles in a day on the equator, so 1,000 miles per hour. That's another kind of angular momentum called spin angular momentum, and that's why you go faster at the equator. When you click a pen to write with it, does it gain mass? Yes. When you compress a spring and it stays compressed, some of the energy that you use to compress that spring gets saved as mass. This experiment has actually been done. They have taken springs and they have compressed them with a force so that the spring stays compressed, and then they weigh it on a scale. And indeed, the inertial mass or the gravitational mass of this system increases by a tiny amount, and it can actually be weighed. It was one of the predictions of Albert Einstein's theory of special relativity that E equals mc squared. And actually, the equation is E equals gamma mc squared. But for an object at rest, it is E equals mc squared. How could a black hole turn you into a graviton or a bunch of gravitons? Well, as you fell into the black hole, you would be crushed, and you would be crushed into such a small volume that all the forces, the Pauli exclusion forces, like the Fermi degeneracy pressure, the electron degeneracy pressure, and the neutron degeneracy pressure, to be specific, because there's two forms, they would be overwhelmed. And so all your mass energy would suddenly be able to pile up into a single state. You would no longer be composed out of fermions. You would be made out of bosons now. And bosons can all pile up into the single state. So you could be crushed into a state that's just basically a point in space and time, and it would be a particle like gravitons, and it wouldn't violate either theory. What's a graviton? A graviton is the particle that would correspond to the gravitational force, in the same way that the photon corresponds to the electromagnetic force. How is it possible for a force to have a particle associated with it? Well, remember, it comes back to that weird quantum mechanical picture where you can have something that acts like a wave sometimes and something that acts like a particle at others. And also, it has to do with the field nature of nature at fundamental levels. Now, the interesting thing is, if it exists, we would expect it to be a spin 2 boson. A spin 2 because the stress energy tensor, which it corresponds to classically, is a rank 2 tensor. So it's like a vector, except it has an additional direction, an additional degree of freedom. And we would expect it to be a boson because, like other force carriers, it can pile up all into one state. A lot of people are confused about gravity. Is it a force or not? Einstein says it's not a force, that it just emerges from space and time being curved. But then we talk about these force particles called gravitons. Which is it? Well, it's important to understand that in Einstein's theory, he thought that electromagnetism would also emerge from the underlying background of space and time. And on his dying day, he died trying to unify electricity and magnetism with gravity. But he was unsuccessful. And he didn't really know about the weak nuclear force, and he didn't know about the strong nuclear force at all. So the situation since Einstein's day has changed. Quantum field theory has completely changed our concept of what forces and particles could be. Stay tuned for more. Can two people eat the exact same number of calories but gain different amounts of weight? Yes. But doesn't this violate conservation of energy? I mean, calories are just energy, right? Yes, it would violate conservation of energy if our bodies were simple thermodynamic engines, but they're not. They're biochemical engines. And in order to gain weight, you need more than just ingesting calories. You need a chemical to bring that energy into your cells, and that chemical is insulin. Two people might make different amounts of insulin in response to the same number of calories, and the person who makes more insulin will gain more weight. As you get older, you tend to develop resistance to insulin, and you may also make more insulin then as well. Today, the first spectacular images from the James Webb Space Telescope have been released. But what is James Webb Space Telescope, and why is this so significant? Well, the James Webb Telescope is an infrared telescope, meaning that it looks at a wavelength of light that is redder than the visible range, meaning that it's too low of a frequency and too long of a wavelength for our eyes to see. However, it can be enhanced once the images are detected so that we can actually see what the telescope is seeing in the infrared, which is what this image behind me represents. Now, why is this important? Well, we can see images from way further back in time than we can with optical telescopes because the light is so redshifted. If the universe is infinite, and scientists think it might be, does that mean that there's an infinite amount of energy? Yes, it would mean that. The answer of whether or not the universe is infinite or not is an open question in cosmology, and it's currently being investigated. As far as we know, it looks to be infinite to us. However, the difference between infinite and really big does make a difference. So more investigation is needed. Here's another interesting thing to think about. When the universe expands, can it create new energy? Well, actually, yes, because in general relativity, there is no energy conservation. It's different than what you might think it is in classical physics. You've heard that the speed of light is 2.9 times 10 to the 8th meters per second. And you've also heard that nothing can travel faster than the speed of light in a vacuum. So is that actually true? No, it's wrong. Although it is said in Albert Einstein's special theory of relativity that nothing can travel faster than the speed of light, recently scientists showed that photons tunneling through an optical barrier could go much faster than the speed of light. Tunneling is a quantum mechanical effect that was not known about when special relativity was postulated. This effect allows particles to quantum mechanically travel in areas that they would be energetically forbidden to classically. Not only photons do this, but electrons do as well, and it's way faster than the speed of light. Was there a planet that was discovered with a pen and not a telescope? Yes. It was one of the biggest mysteries in the 1800s. John Couch Adams and Urbain Le Verrier looked at the orbit of Uranus, and they found that there was something wrong with its path. It wasn't orbiting in the way predicted by Newton's laws of gravity. What they postulated was, what if there was a missing planet that they didn't know about that was somehow affecting its orbit? What they did was, they took data of Uranus, and they compared it to the path that it would follow if there was no other object there besides the sun and the planets that we knew about. And what they found was its orbit could only be predicted if there was another planet somewhere further out influencing it. They actually calculated the mass and the coordinates, and they sent this to an astronomer who discovered it with a telescope. Why is there so much more matter than there is antimatter? We think that the reason why is because of a process called spontaneous symmetry breaking. You see, when the universe was young, there was equal amounts of matter and antimatter. And we can represent that energy distribution as the top of the sombrero, where everything is symmetric. You see, this sombrero function can represent all the possible energy configurations of our universe. But shortly thereafter, something happened and things were set off balance just a little bit. And we rolled down the hill all the way to the bottom, breaking the symmetry. We now have way more matter than we do antimatter. This process occurs and it's called spontaneous symmetry breaking, and it can be observed in many other systems as well. Jupiter has an amazing and deadly secret. It emits huge amounts of radiation, and it's caused by its incredibly powerful magnetic field called the magnetosphere. In fact, it's so massive that if you could see it, it would be 5 times larger in the sky than the moon. This magnetic field is generated by the core of Jupiter. It has a molten core of liquid hydrogen, and there's a massive amount of electric current that flows through it, producing these magnetic fields. They are 20 times stronger in magnitude than the Earth, but 20,000 times stronger of a magnetic moment. That's because the area of Jupiter is so much more massive than Earth. What is this crazy object behind me? This is Io. It's a moon of Jupiter, and it orbits roughly 420,000 kilometers away. The colors that you see are the result of all these volcanic eruptions. You see, it has over 400 active volcanoes that regularly erupt and litter the surface with sulfur and sulfur dioxide. And the eruptions can go as high as 500 kilometers or 300 miles above the surface. What causes all of these volcanoes to exist is frictional forces within the interior. Plates push up against each other just like they do on Earth, causing volcanoes. But the forces are due to tidal forces between Jupiter and its other moons. What's a parsec? Well, it's a unit of distance used in astronomy. But let me show you how it's defined. So, here we have an orbit of the Earth around the Sun, represented by this circle here. The blue represents the Earth. If we measure where some star is located in the sky at some time of year, and then 6 months later, when we're on the other side of the Sun, we measure where that star is now, we have an angle in the sky. We can divide that by a half, and then we have this angle of this right triangle. We know the leg is 1 AU. So knowing the leg of 1 AU and that distance in the sky is enough to tell us what this other leg is, the distance from the Sun to the star. And thus, if we have an angle subtended of 1 arc second, we have a distance of 3.26 light years from the Sun to the star, and that's a parsec. Get ready for a solar storm. In mid-July, astrophysicists spotted a huge solar filament that stretched 238,000 miles or 384,000 kilometers long and was 12,400 miles or 20,000 kilometers deep. This canyon of fire, as it's known, is actually hot gas called plasma. It's so hot that the protons and electrons separate and it becomes highly charged. Now that this filament has broken, there's a huge coronal mass ejection that's occurred. This is an explosive jet of charged particles that goes right towards Earth. These solar storms, as they're also known, are disruptive to satellites because they don't have the protection of Earth's magnetic field. But we should be fine. JWST just captured the oldest galaxy ever seen. Glass Z13 dates to just 300 million years after the Big Bang. For context, that means the light was emitted more than 13.4 billion years ago. But why does the galaxy look like this? Well, it's extremely redshifted because it's so far back that the universe has expanded a lot since the light was first emitted. It's also pixelated because it's so far away that it's difficult to resolve. But despite these limitations, there's a lot that we can learn from it. For example, it's much smaller than the Milky Way. That's interesting because early galaxies were thought to be populated by extremely massive stars. So this is a very interesting finding in the context of galactic evolution. Recently, a viewer asked me, is gravity equal to time? And I thought about it for a second in terms of how to answer it. And I realized the best way to look at it is that time is not equal to gravity, but a curvature in time and space is. And what happens is, with Einstein's theory, we can see gravity emerging as space and time curve under the influence of energy. And for Earth's gravitational field, we have GPS satellites orbiting much higher up than we ever had before. And when we look at the clocks, the time measurements for those don't match when those satellites are on the ground. So the rate of passing of time is different for these satellites when they're at different points in the gravitational field. And that's the curvature in time of gravity. In general relativity, is there something more fundamental than conservation of energy itself? Yes, geometry is more fundamental, and the geometry of the manifold determines the energy conditions and the energy conditions that are obeyed. For example, if we live in a universe that is continually expanding and never bounded, then that manifold could be one in which energy conservation is not respected globally, but it's still respected locally. And what that means is that at vast scales, global scales for the giant space of the universe itself, energy conservation might be violated by new energy being created. But locally, in our local region, certainly on Earth, energy conservation would still be respected locally. These are very important concepts for understanding manifolds in the universe. Images of the Phantom Galaxy have just been released from James Webb Space Telescope, and a lot of sources are saying it's a wormhole. But is it? This is actually an image of NGC 628, also known as Messier 74. This has been imaged many times before by Hubble, and what makes it so interesting is that it has a near perfect spiral. It's also thought to host a very large intermediate mass black hole. The images that you see of it spiraling are caused by angular momentum. That means that this galaxy has a massive amount of rotation that's synchronized. The galactic dynamics that causes galaxies to form spirals is still under debate, but we've made a lot of progress. A wormhole is not necessary to create this kind of a spiral, but it's a fun idea. Okay, so there's this crazy reason why we can't actually observe the Big Bang, and it has to do with this thing called photon decoupling time. You see, when the Big Bang happened, the universe was so hot and energetic that light couldn't be separated from the other fundamental particles. It was all this big hot plasma. But approximately 300,000 years after the Big Bang, you see the universe is expanding this whole time. So the energy density of every square cubic meter of space is going down. And once that energy density went down enough, the light was actually able to decouple from matter and travel off on its own. And then we were able to finally start observing features. Now, there's a few other reasons why we can't actually observe quite that far back yet, but that's approximately the time when we can observe the universe. Is there a difference between something being a liquid and something being a fluid? Yes. A liquid, by definition, is a substance that contains a constant volume independent of pressure. And a fluid, meanwhile, is something that can flow and obey the fluid differential equations of motion. So it's a continuum substance. That means that both gases and liquids are fluids. And in a sense, we live at the bottom of an ocean of air, for example, because all of the air and gas above us is a fluid that flows. And in some cases, we can even approximate galaxies and stars moving within the galaxies as fluids. I want to comment on this interesting post by Theoretical Mass. Is it true that when you touch an object, you're really only 10 to the minus eighth meters away from it, and that all you ever actually feel is the force of repulsion? Well, yes, it is true that the outer electrons of whatever you're touching interact with that object, and that's actually electrostatic friction, and that this frictional force is what allows you to sit in a chair without sliding out and allows us to stand and even walk. It's very fascinating to think that the friction that you always hear about classically actually has this really microscopic origin. What's interesting is there's fluids that lack viscosity, and viscosity is kind of like the friction for a fluid, and they can actually flow up the sides of a tube and flow out of a tube because they don't have viscosity anymore. They're called superfluids. What are the Einstein field equations really? They're directions for how to make a four-dimensional map. If there's no gravity and no energy, we just have a flat map. There's no curvature to it at all, but there's four dimensions, 3 of space and 1 of time. But if you add energy, then you start to curve that map, and that curvature of that map is the source of gravity. It's all encapsulated right here in Einstein's field equations. What this says is that energy curves space, and we can measure this curvature as a deviation from the vectors that describe space and time. They deviate from a flat space by a certain amount. The greater the deviation, the more gravity there is. If we have singularities of any kind, we have a hole in the four-dimensional space, and that's a black hole. Now, the Einstein field equations are tensor equations. Tensors are vectors, but they're generalized to any dimension. They can be 0 dimension, which is scalars, 1 dimensional, which is vectors, 2-dimensional, 3-dimensional, and other higher levels. The dimensionality of it is given by the number of indices that it has. You can see these tensors have indices in this equation here. The interesting thing is that the disagreement between flat space and curved space is what gives us gravity. These equations are very powerful and they're very general. They can be used to describe the geometry around Earth, the sun, or even much more gravitationally intense objects such as neutron stars, black holes, and other things. Carl Schwarzschild was able to actually recover Newton's equations from these when he used the potential for something like the Earth.
10, 9, 8, 7, 6, 5, 4, 3, 2, 1.
Imagine an experiment where you're the Schrodinger's cat. That's right, you're inside the box, and there's a 50% chance that a quantum mechanical result will cause gas to be released. But you're in a superposition of living and dead. And on top of everything, the many worlds interpretation of quantum mechanics holds, and every time that you do die, there's a portion of your wave function that goes on living for infinity. That's quantum suicide and quantum immortality in a nutshell. It's a thought experiment, and mathematically, it holds in the formulation of many worlds theory of quantum mechanics. If you give me just a few seconds, I can teach you everything you need to know to understand the concept of parallel universes. Ready? Here goes. The plot you're looking at here is called a space-time diagram. There's 2 cones. One of them is the future light cone, and the other is the past. At any given point in time, we're located at the origin. Now, when the Big Bang happened, you can think of it as the moment when these cones were created. But at the same time, there could have been other light cones created, creating other universes. But, as you can see here, there's 3 distinct regions. There's the time-like region, which lies within the light cone, the light-like region, which is at the actual surface of the cone, and the space-like region. You guessed it, light travels on the light-like region, we travel within the time-like region. But to travel to the space-like region, where the other universes are located, you'd have to go faster than the speed of light. Is the wave function real? That's the topic for today's video. The wave function is the mathematical object that describes the complete state of something quantum mechanically. A lot of people, including people involved in physics even, think that the wave function is really just a mathematical tool, that it doesn't really describe the object. However, there's an experiment to make you think twice about this. There's a device called a scanning tunneling microscope where the electron's wave can tunnel into regions where it's energetically forbidden to be. And it can only do this because of its wave-like properties. So that'll make you think twice when you question the wave function. How do we measure the mass of the sun? Start with Newton's universal law of gravitation. That's equal to big G, Newton's universal constant, times the mass of the sun, times the mass of the earth, divided by r squared, where r is the distance from the earth to the sun. But we also remember that force is equal to mass times acceleration. That's on the right-hand side. We have the mass of the earth times acceleration, which is v squared over r. V is the velocity of the earth, and that's squared, and then we divide that by the distance from the earth to the sun. That's r. Then we can cancel out some terms, and we end up with the mass of the sun, big M, is equal to the distance from the earth to the sun times v squared over big G. V squared is just the velocity of the earth squared. This gives us that the mass of the sun is 2 times 10 to the 30 kilograms. What does it actually look like when a galaxy merges with another galaxy? Well, here I'm using a simulation to show a galaxy that we start with. We have a bunch of stars tightly bound gravitationally at the center, and then other stars orbiting outward on the exterior of the galaxy. Now what I'm going to do is I'm going to create another galaxy similar to this one. I'm going to create a galactic center where we have a bunch of stars orbiting really close together. That's what I'm doing right here in this point right there. And then I'm going to create more stars orbiting on the outside. And then you can just imagine that these two galaxies come together from some distance, and now we're seeing how they interact gravitationally. So here we have the gravitational interaction. You can see that some of the stars' orbits become very eccentric. They go way out, but pretty soon the galactic centers merge into one galaxy. All right, this is a response video to one I posted about scientific progress and a lack of funding. So, were the lunar missions a major scientific advancement? That depends on what your definition of a scientific advancement is. If your definition of a scientific advancement is something like the equation E equals mc squared, or the development of quantum mechanics, or even the development of nuclear energy, then no. Unfortunately, the lunar missions was not a breakthrough on that level. We used essentially the technology developed by V-2 rockets, which was during World War II, unfortunately by not the good guys. And we implemented this to get us to the moon. I would say it was a major engineering advancement, and it had never been done before, so I don't want to take away the greatness of that, but I don't think that qualifies as a scientific advancement on the level of like something that would happen in a golden age of science. Somebody recently asked me, what would it actually feel like to fall inside a black hole? Well, as you approached the black hole and got closer and closer, the passage of time for you compared to an observer far away from the black hole would change immensely. Time would go much slower for you than it did when you were far away from the black hole. But you wouldn't notice this at all. You wouldn't have any perception of the time passage changing. You can't perceive that. However, you would perceive the intense tidal force, which is caused by the force of gravity from the black hole being much stronger on your feet than your head. The gravitational field of a black hole is so strong that a significant tidal difference or a tidal force exists, and it would literally snap you in half. What is lightning and what causes it? Lightning, a form of plasma, is created when you have a cloud that has ice crystals carrying positive ions upwards, and hail that's a little bit heavier has negative ions going downwards. These charges become separated. This is due to the fact that all this water vapor that's in the atmosphere is very polarized. When you have a lot of heat and energy in the atmosphere, this process can occur, and it can cause the top of the cloud to become very positively charged and the bottom to become very negatively charged. This leads to the formation of a plasma-like substance where we have freely charged electrons moving about. Now, air has a certain permittivity, meaning that there has to be a large potential in order for the electrons to freely flow through it, but eventually that can occur and you have a lightning strike. Supporting human life on dwarf planet Pluto might not be as difficult as it seems. The extreme cold temperatures have their advantages. For example, we have superconductors which conduct electricity in a circuit with no resistance. This means that there's no energy losses as the electrons flow. We could potentially build these superconductors on Pluto, and we wouldn't have to use an enormous amount of energy to keep them cool enough because the temperature would already be optimal for their performance. Whereas on Earth, it takes a tremendous amount of energy to keep these superconductors cold enough. Additionally, we might be able to use electrochemical methods to actually make liquid water out of the ice and maybe even oxygen to produce an atmosphere eventually. Recently, one of my viewers asked me, does an electron orbit the nucleus in an atom? And the answer is no. However, it's complicated because while the electron does not orbit the nucleus in a classical sense, meaning it completes orbits at some specified time frame, it does have orbital angular momentum as well as spin angular momentum. Now, if we want to make a classical analogy, the spin angular momentum would be the Earth spinning about its axis, and its orbital angular momentum would be the momentum it has from orbiting the sun. So there's two types. The electron has these types, and yet it does not physically complete orbits. So how is this possible? Well, this is because of the strangeness of quantum mechanics. The electron actually has no definite position, so it can't have a classical momentum in this sense. Another reason why we can't say that the electron is orbiting the nucleus in an atom is because it doesn't have a definite orbital angular momentum. It has a superposition of different possible angular momentums. The eigenstates are in a superposition, and then if we disturb the electron and make a measurement, then it has one of these values. But we can't treat it as if it has a definite value because then the mechanics of it doesn't work out properly. So we have to treat it as if it's in a superposition of different angular momentum states, both for orbital angular momentum and spin angular momentum. So it can actually be spinning up and down simultaneously. That's incredible, and that's impossible classically, but happens in quantum mechanics. If the electron doesn't have a definite position or momentum, then when is it more like a particle and when is it more like something else? Well, when we measure the electron, we actually disturb it, and it does acquire a more definite position then. So in this sense, it's like a particle when we measure it, but when we're not measuring it, it moves around more like a wave. It distributes itself in a wispy, uncertain type of orientation where it can be in multiple superpositions. One final point, why doesn't the nucleus behave like this? Why is the nucleus more centered? Well, the nucleus is actually made up of particles too, but the forces that confine these particles that make up the nucleus, like the protons and neutrons themselves, they're bound by a much stronger force, which gives them a more certain position so they can't wave. What is spin actually? Spin is a fundamental quantum property that every particle possesses, and the type of spin that it has determines the behavior that it exhibits. For example, we have something called the Pauli exclusion principle that electrons obey. Electrons are fermions with spin 1/2. Any particle that has a spin of 1/2 or like 3/2 or 5/2 is a fermion. These particles cannot occupy the same quantum state. What this means is that atoms have to have electrons with distinct energy levels, and they can't all pile up in one giant blob of energy. So it helps determine the size of the atoms. Meanwhile, photons, which is light, are bosons. They can all pile up in the same quantum state, and that's why we can make lasers with them. Does a quantum particle, like an electron, ever lose its spin angular momentum? No. Incredibly, unlike a classical object that's spinning about its axis and can lose its angular momentum due to a variety of interactions like friction or even gravitational interactions, if we're talking about the moon, which at one point did spin about its axis but became gravitationally locked. Unlike those objects classically, the quantum objects that have this intrinsic spin, they never lose this spin. It's like a source of energy that never depletes. It's intrinsic to them in the same way that we think of mass as being intrinsic to an object. So what makes this happen? Well, this is due to the quantum mechanics of the objects. And we can encapsulate this in the wave function and saying that the wave function is either symmetric or anti-symmetric. WASP 12b is a fascinating exoplanet. It's a hot Jupiter, so it's a very large gas giant planet, but unlike the Earth, it orbits extremely close to its parent star. In fact, it's only 1/43rd the distance of an astronomical unit, which is the distance from the Earth to the Sun. So it's many times closer. It's so close, in fact, that the parent star causes these incredible tidal forces that cause it to bulge and get stretched. Here's another impression of the planet. It might be that the side facing the star actually catches fire. It's so close. So we have asteroids, and the question is, how often do they strike the Earth, and what is the risk? So it turns out that asteroids do strike the Earth pretty often, but most of them are pretty small, and when we talk about an Earth strike, we should really be more precise and say they explode in the air generally, because the atmosphere causes them to break up and explode before they ever even touch the ground. However, fragments can then later land onto the Earth, and they are often discovered. However, there was an event in June 30th, 1908, where an asteroid flattened 80 million trees and basically completely demolished 830 square miles. For perspective, if that had hit Los Angeles directly, it would have completely destroyed it. The asteroid was about 200 feet in size, and it actually broke up in the atmosphere and exploded, so it never actually struck the ground either, but it did a ton of damage. What are the Einstein field equations really? They're really directions for a map of four-dimensional space. Just like you can have a map of the Earth that maps out the continents and where they're located in relation to each other, you can also make a map of the four-dimensional universe. What's interesting is that mathematically, this is achievable with 3 spatial dimensions and 1 dimension of time. But you do need that time dimension because, as we've talked about before, time depends upon various properties of space, and it changes in relation to those and in relation to the influence of energy in different locations. Here's the Einstein field equations in all their glory. Now, this equation is incredibly general. As you'll see, there's these funny symbols, mu and nu, the thing that looks like a U almost and a V. Those are subscript indices, and what those denote is the dimensionality of the object called a tensor. You see, a scalar is something that just has a magnitude. It's a rank 0 tensor. A vector has a magnitude and a direction. It's a vector. A tensor is anything that's those or higher dimensionality, like 2 or 3 different directions. And these things can become infinite. It just depends. With Einstein's field equations, it's apparent that we can actually achieve the relations with mostly rank 2 tensors. Now, what this actually describes is how flat space is related to the curved space. In other words, if we have gravity, the flat space and the curved space disagree with each other. Basically, we need a way that we can describe all the relations of the vectors so that they stay consistent. And to do that, we need the tensors that relate the curvature from one component to the next, because they'll change as we go from place to place. We do that with the Riemann curvature tensor. and then we can contract that and make the Ricci tensor, and ultimately produce the Einstein tensor, which makes the Einstein field equations. The details are kind of mathematical, but the important thing to keep in mind is this is a map in 4 dimensions, and if there's a break or a discontinuity in the map, that produces a black hole or a wormhole. And these discontinuities are singularities, or places that are disconnected from the rest of the map. In the early universe, when stars first formed, they were much more massive than they are today on average. This is an image I created of 3 early stars. Here you can see that they're a bright blue color. The reason for that is because these stars are much hotter than our own sun is, and they emit at a peak wavelength that's much smaller and more blue. This is true for any star. The hotter the star, the more its wavelengths will be shifted to a bluer range. Now, the reason these stars got so massive is because in the early universe, we only had 2 elements, hydrogen and helium. So these stars started out being made out of exclusively just these elements. These elements are much harder to cool off than if they have heavier elements in them as well. The end result is that more mass was required in order to overcome the thermal pressure and form into a star. Why were massive early stars so much bluer than our own sun? The answer lies in these curves here. You see, at a higher temperature, the peak wavelength shifts to a smaller value. Blue wavelength light is shorter than red, for example, or orange. And so these massive blue stars in the early universe were much hotter than our sun. This is Wien's law. This is the equation that explains what the peak wavelength of the light is. That's lambda max. That's essentially the color that the star will be because it peaks at that wavelength. B is just a constant of proportionality that's measured experimentally, and T is the absolute temperature. You can actually use this formula to figure out what your peak wavelength is. Pretty cool. And you'll see that it's in the infrared range of radiation. Why were early stars so much more massive on average than stars are today? Well, the answer has to do with quantum mechanics. You see, in the early universe, only hydrogen and helium were available for these stars to form. However, hydrogen and helium have only 1 or 2 electrons respectively, and this means they have fewer energy levels. And so there's not as many ways for these gases to radiate away their energy. And radiating away their energy is critical because stars can't form unless a gas cloud can radiate away its energy and get cold and gravitationally collapse under its own mass. So the early stars had to be much more massive because they had a lot more radiation pressure because the hydrogen and helium from which they were forming was just hotter overall. So these stars were maybe 100 times larger than our sun is today. What level of radiation exposure can an astronaut expect to experience while in space? During a 6-month mission, an astronaut can expect to receive anywhere from 50 to 2,000 millisieverts of radiation exposure. For comparison, the biological damage to the human body has been documented starting at around 100 millisieverts. So you can see where the upper range of 2,000 millisieverts of radiation exposure is a bit of a concern. Of particular risk is when astronauts go on these types of spacewalks pictured here, where they're actually openly exposed to the atmospheric radiation from cosmic rays bouncing off of Earth's atmosphere and also directly from the solar wind from the sun. Luckily, NASA has been conducting research to make spacesuits much safer for future missions. Investigations are currently being made to make more protective materials for future missions. Without a doubt, the most dangerous forms of radiation are HCE ions, and these forms of radiation are the kinds that astronauts can experience in space. What makes these so dangerous is that they're incredibly fast moving, and they also have a lot of mass, so they carry a lot of momentum. But why do they have so much mass? Well, to start with, this form of radiation is not a photon. It's actually the nuclei of atoms. It includes the nuclei of atoms such as helium, carbon, oxygen, magnesium, silicon, iron, and even as high up as uranium. High energy photons knock electrons away from neutral atoms and ionize them, leaving only the nuclei remaining. These nuclei are then charged and they're accelerated by magnetic fields and thrown towards Earth. All right, everybody, gather around for the amazing, tragic story of Vulcan, the planet that was not meant to be. In the early 1900s and 1800s, scientists thought that there was a planet nicknamed Vulcan that was inside the orbit of Mercury, even closer to the sun than Mercury. Why did they think this? Well, Mercury went on an orbit that was not closed. It experienced perihelion, which means that after it completed 1 year, it wasn't in exactly the same space. Here you can see two hypothetical orbits of Mercury in blue and green shown going around the sun, and Vulcan in that inner orbit. Vulcan was supposed to be the reason why Mercury was experiencing this perihelion. It was thought that Vulcan was disturbing its orbit. They had reason to suspect this because this was actually what was going on with Pluto and Neptune. However, it turned out that this effect was actually caused by general relativity. All right, let's answer a question. A viewer asks, in regards to dark energy, everything is growing. Does that mean particles are getting larger or their existence skipping across diverging space-time quanta or neither? Well, dark energy is the energy that goes into causing new expansion of space and time. And as far as we know, that may not obey energy conservation. The photons and other particles do obey energy conservation relations. Photons, for example, from the early universe that form the cosmic microwave background radiation are stretched out with the expansion of space and redshifted. So to answer your question, these particles are affected by the expansion of the universe, but they're not given more energy. It's just that the overall volume in which they exist is expanded and increased. So they respond to the dark energy, but not in a way that gives them more energy. All right, let's answer some questions. A viewer asks, is dark energy consistent with Newtonian physics laws that say that energy can't be created or destroyed? This is a really interesting question. It turns out that the first person who discovered dark matter accidentally was Einstein when he wrote down the field equations for the universe. But the term that had dark energy in it, he thought was just mathematical and not actually physical. So he added a term, a lambda term, to balance it out and make it so that the universe was static and didn't expand. But when they later discovered that most of the universe is redshifted and expanding away from us, they went back to those equations and found out that the dark energy does exist and it doesn't conserve traditional energy conservation theorems like we have in classical physics. It's incredible, but it's true. And actually, at really short scales, energy conservation can also be violated in quantum field theory. What is this crazy photo? This is a picture of an astronaut doing a spacewalk and making a repair to the alpha magnetic spectrometer. This instrument measures antimatter, specifically positrons originating from energetic events such as cosmic rays coming in. What's fascinating is there's no preferred direction to the positrons that are being detected, which could indicate that dark matter is actually responsible for some of the positrons. While it's still a work in progress, the background radiation of positrons coming in shows that there's no preferred direction, meaning it could be originating from dark matter and anti-dark matter in the galaxy halo of dark matter, and that produces the positrons. That's one possibility. A brand new documentary on YouTube about observational detection of dark matter. Check it out. All right, let's answer some questions. A viewer asks, why do electrons exist as a probabilistic wave function, but protons and neutrons not? What accounts for this difference? Actually, everything exists as a probabilistic wave function, even you, but there's a reason we can't observe it in larger objects. Even it's harder to observe with protons and neutrons. The equation for the matter wave is behind me. Notice that the momentum is in the denominator. That means the more massive an object is, the smaller that wavelength is. We can actually use electrons as microscopes because we can diffract off of their matter waves. Their matter waves are so large, we can actually use them. However, more massive objects have much larger momentum. And remember, that thing in the top is Planck's constant. So it's really easy to shrink it down. And even our own bodies have a matter wave, but they're too small to observe. Hey everybody, don't forget to check out my new YouTube channel. I've got an hour-long documentary on there. I promise you will love it. The link is in my bio. Instagram won't let me put a clickable link in my posts, unfortunately. So just go right up to my bio on Instagram, click on the YouTube, and if you like what you see, click and subscribe. It really helps out. Thanks again for all your love and support. Peace. All right, enjoy this latest clip from my brand new documentary on dark matter out now on YouTube. Click the link in my bio and watch the full thing. It's an hour long. I promise you will love it. Now, interestingly enough, there's actually a lot that we can learn by how big galaxies are. Because if the dark matter particles that form the majority of our universe and our galaxies were fast moving, like, say, neutrinos, which are dark matter that travel almost at the speed of light, well, then we wouldn't have all of these types of gravitationally bound structures forming, because the dark matter would have too much kinetic energy to be gravitationally attracted to any meaningful size. So the fact that we have these large structures and these galaxies forming even in an early time in the universe points to an identity for a dark matter particle that is massive and also slow moving, hence the term cold dark matter, as opposed to hot dark matter, which would be a fast moving form of dark matter, like a neutrino. What is lambda CDM? If you read about cosmology, you'll see this term lambda CDM pop up. What it means is, it means a universe where we have dark energy and dark matter. The dark energy is represented by the lambda term. That's because when we have the Einstein field equations, we have a lambda in front of that term that gives the expansion for the metric, and essentially the dark energy is associated with that term. The CDM just stands for cold dark matter. The fact that we think that the majority of the dark matter in the universe is low velocity so that it's not moving relativistic speeds, so it clumps at a certain point and causes galaxies to form and serves as the main gravitational potential. If you want to learn more, check out my latest documentary on YouTube. There's a link in my bio. Thanks a lot for watching and have a great one. Are X-rays safe? Is it safe to go to the dentist and get an X-ray for your mouth? Is it safe to go to the doctor and get a CAT scan? Well, the thing about it is that yes, it's safe, but I want to explain why it's safe and why it's not safe to get a lot of X-rays, because it's a little bit more complicated than you might think. So first and foremost, Einstein figured out that to ionize something, to knock an electron off of an atom, it's not the intensity of the radiation that matters, it's the frequency. So what happens is it takes a single photon of light to ionize an atom and knock the electron off of it. That's also how DNA is damaged. So that's why it's relevant to the topic of X-rays. So what you're thinking is, wait a second, when I get an X-ray, those X-rays are strong enough to knock electrons off of my cells, right? Because they're strong enough to penetrate through. Are they strong enough to do damage? And the answer is maybe. They might be strong enough under the right circumstances to ionize your cell, an electron in your cell. But here's the thing. They've dialed it in, the radiation levels, that is, on these machines, so that they really don't use that many photons. They use a very low intensity of, somewhat high frequency X-rays to do the imaging. But the thing is that our bodies have evolved to repair damage done by this kind of radiation, because we get that kind of radiation from natural sources too. We get it from the sun and we get it from soil. The ground gives off radiation and every human gets exposure to it. But the thing is our bodies can repair very minor damage to our cellular DNA, with the exception of a few people. There are some people where that, for some reason, that mechanism is hindered and they're very much at risk for cancer. And if they have those genetic conditions, they're not advised to get an x-ray. Another example is somebody who's pregnant, because if the fetus is developing, the cells are dividing particularly rapidly and they're very vulnerable to radiation. They can't protect themselves like a normal adult or even a child's cells will be able to repair the kind of minor damage you get from an x-ray. But the whole point is that these machines are incredibly safe because they use a low intensity, and even if there is a little tiny bit of damage, your body will repair it. 841 million miles away from Earth and about 759 miles from Saturn lies the moon Titan. Titan is the second largest moon in our solar system. It's 80% more massive than our moon and 50% larger in diameter. But the most incredible thing about Titan is that it has this thick atmosphere. In fact, its atmosphere is mostly made out of nitrogen, which makes it very similar to the atmosphere on Earth. But there are many differences as well. The biggest difference is that Titan does not have any oxygen in its atmosphere. So the other difference is that it contains a larger amount of other components like ammonia, and it has a weather cycle because of this atmosphere and also because of its components. And as a result, it rains, and it has liquid hydrocarbon lakes on the surface that were revealed when the Cassini space probe looked at Titan in more depth. It has orange skies, so if you were on the surface, you would see this thick orange haze. It's difficult to say what the visibility would be on the surface because we don't have very clear pictures of the surface, but there is some limited concept and pictures of the surface at this very moment, and there will be more in the coming future for sure. The other thing that's very fascinating about Titan is that it's actually proof that a moon could sustain life, because there was a debate about the size that an object would need to be in order to hold on to gases. And we pretty much know what the limit is for size in order for something to have an atmosphere. But Titan shows us that a size does not have to be nearly the size of the Earth in order to have a sustainable atmosphere. So that's an incredible result. Now, it is true that because of its size, it has very fewer components like hydrogen and other things like that, because they just escape. It doesn't have the gravity to hold on to those kinds of gases. But Earth is also similar to that. That's why we don't have helium and hydrogen in our atmosphere on Earth, because of the size. It just escapes. There's an experiment that's been done with particles like photons or even electrons that's so insane you won't believe it. So there's this quantum mechanical property called spin, and it's a type of angular momentum. The classical version of it is the spinning of the Earth, because the Earth has angular momentum in terms of its orbit around the sun. That's orbital angular momentum, but it also has spin angular momentum. Well, in quantum mechanics, there's an analogous property, but it's different than in classical physics. You see, with this spin, it's like it always has a value, and it's either spin up or spin down when it interacts with a magnet, but nothing in between. It's completely different than classical physics where you have a continuum of values. It's either up or down, and this was demonstrated with an experiment called the Stern-Gerlach experiment. Okay, so let's say that we have two particles, like two photons, that have one is spin up and the other is spin down. But we don't know which one is spin up and which one is spin down. We can't treat it like as if the system, one of the particles has spin up and the other one has spin down the whole time. We have to treat it as a superposition where the particle doesn't have a specific value of spin until we measure it. That's right. It doesn't matter how far these particles travel away from each other. If they're in an entangled state, they do not have the specific property of up or down until we measure it. And they can be on other sides of the universe, through a wormhole, whatever you want. It doesn't matter. Until they're measured and a value is found, their value is indeterminate. As soon as the measurement is made, the other particle immediately takes on the other value. This property of superpositions and particles suddenly getting values is what Einstein called spooky action at a distance. Because in physics, any process is supposed to have causality, and it's supposed to have a length or duration of time in which to occur. And because these spin entangled systems collapsed and there was no duration of time, he said that couldn't be possible. That's spooky action at a distance. But it was later demonstrated in experiments to be the case after he had died. As recently as the 1980s, and even more recent than that, these spin experiments with collapsing wave functions and the particles being known happened. In addition to this triple star system, there's actually exoplanets orbiting around some of these stars. So the littlest star, the red dwarf, has at least 3 known exoplanets, and one of them's an Earth-sized planet in the habitable zone. Now, it's a red dwarf star. Red dwarfs are much less massive and much less luminous than our sun. So in order to be in the habitable zone and get enough heat, it has to be much closer. And it is. In fact, it completes an orbit in only 11 days. Now, if there's actually things living on this planet, they're going to see a star that takes up a huge amount of the sky. It's going to be much more massive. It will be an absolutely incredible view and an incredible planet to be on. There's an incredible triple star system called Alpha Centauri, and it's 4.3 light years away from us. Now, there's 3 stars. The first one is called Alpha Centauri A. It's 1.1 times the mass of the sun, and it's 1.5 times as luminous. So it's brighter than our sun. And the next one is called Alpha Centauri B, and it's 0.9 times the mass of the sun and about half as luminous. These 2 stars are 35 AU away from each other. So they're not the same brightness exactly, but they're very close. And there's also a third star. It's a red dwarf, and it's called Proxima Centauri, and it's 13,000 astronomical units away. So it's way further away than the other 2. How big is the sun? Well, it's 865,370 miles across, over 1 million kilometers across. That tiny little dot at the center, in between the top line and the bottom line, is our Earth in comparison to its size. Wow, that's amazing. Another issue where quantum mechanics doesn't agree with relativity is in the spin of a particle. Because if the electron was spinning in a classical sense, it would create this sort of frame dragging effect that you can see here in this image. But the issue is spin is not a classical spinning in the normal sense. In fact, you have to actually rotate twice around to end up in the same spot that you're located. So a 360-degree rotation, you do not end up in the same spot as where you started, like you would in classical space. This is yet another disagreement between quantum mechanics and general relativity that is still yet to be resolved. Okay, so I wanted to sort of illustrate this problem of quantum mechanics and relativity. So I'm going to start with an electron. So here we have a single solitary electron. According to a classical theory like general relativity, we could picture this electron as a solid object, even if it's very tiny. This is how the electron was viewed in the early 20th century. If this is the correct picture of an electron, the gravitational field associated with the electron should look something like this. As you can see here, the electron's mass is sort of bending the space and time around it. These coordinate grids could just represent measurements, and so you can see that there's a gravitational field associated with this electron. But this was shown to be wrong. The electron does not have a definite position. At any moment in time, it has a probability cloud associated with it. You can see how ridiculous this definite coordinate system looks when superimposed on this probability cloud. In my new book coming out shortly, I'm going to talk about a disagreement between the Einstein field equations pictured above and the Heisenberg uncertainty principle. While the Einstein field equations say that the gravitational force is due to a mass bending space and time at a precise location, the Heisenberg uncertainty principle says that the precise position and location of an object can never actually be known. There's always a quantum uncertainty due to the effect of the object behaving like a wave. But this is a problem for both theories because we have to know the precise location of an object to know its gravitational effect. For example, an electron would still have a gravitational force associated with it. But if its position is uncertain, that would mean that its bending of space and time is uncertain. So this is a major unresolved problem in physics. Today I'm going to talk about an apparent paradox in relativity and its resolution. That's right, today we're going to talk about what is the length of a photon. So here we have the formula for length contraction. L0 is the length of the object in its moving frame. L is the length of the object as measured by a person at rest. As you can see here, the formula will show a shortened length for the object if it's measured in a rest frame because the original length L0 is multiplied by that factor in the square root, so it's less than 1. But a photon goes at velocity of c. Having a look at this formula again, that would give 0 for the term inside the square root. A length of 0? How could a photon have 0 length? It doesn't. This formula doesn't work for a photon because the photon has no reference frame where it's at rest. So this is only valid for massive particles. The Cartwheel Galaxy is a very distinctive galaxy that was recently imaged by James Webb Space Telescope. Behind me is a simulation of its formation. Now, this was caused by a Milky Way-like galaxy that had a smaller galaxy crash into it, and the gravitational field from the smaller galaxy caused the stars from the Milky Way-like galaxy to get all spun up. This simulation was done by Chris Mijos and Sean Maxwell of Case Western Reserve University, and it shows this incredible process in action. If you give me just a few seconds, I can explain parallel universes with the plot behind me. Ready? Here goes. The plot here represents our universe at any time. The past is the cone pointing downwards, and the future is the cone pointing upwards. We're right at the origin at any given instant. We cannot travel outside of this cone. Now, at the time of the Big Bang, you can think of this as the creation of these cones for us. But at the same time, there might have been an infinite number of other cones created that we cannot access. We can't travel to them because they would lie in the space-like region. Because we cannot travel to these potential universes, they're called parallel, like lines that we can never cross. Could a black hole be thought of as its own kind of fundamental particle? Yes. Incredibly, it might not be that inaccurate to say that a black hole is a special kind of fundamental particle. When we think about the fundamental particles of the standard model of particle physics, like electrons and muons and other fundamental particles, these objects often behave like point particles. They don't have a finite extent. They're like infinitesimally small. It's only when these fundamental particles interact with other objects, other types of fundamental particles, that they get a finite volume, like when an electron interacts with the nucleus of an atom to make the volume of like a hydrogen atom. And you might be thinking, well, what about a neutron and a proton? Those have like a radius that's been measured. Well, those are not fundamental particles. The neutron and the proton are actually composed out of quarks and gluons. And quarks and gluons have never been observed go freely about for other reasons, but not only that, but not limited to just the fact that the nature of the gluons is very different than, like, say, the force that describes the electromagnetic force of the electron. The gluon force is the strong force. It's very hard to pull these things apart. Some would say it's infinitely hard. It's still a little bit of a debate, but again, this point-like nature might be one of the reasons for that difficulty. So gluons might behave like point particles too. We don't really know. But the whole point of this is that the black hole is a singular point in space and time. And it's incredible to think that something as complex and different as a black hole might be analogous to an electron or something like that in a weird way, that it has the same spatial extent of being a point. So you could almost think of a black hole as a type of fundamental particle, but you won't see it listed in the standard model of particle physics. Well, why is that? Well, there's a number of reasons. First of all, you can't create a black hole with any other theory of science other than general relativity. And the standard model of particle physics is not compatible with general relativity. So right now, black holes are a general relativistic object outside of the domain of the standard model of particle physics. So that's one reason why you won't hear a black hole called a fundamental particle. But it's interesting to think about. Star mergers happen when two stars get close together and they actually merge into one giant star. This is a very dynamical event, and it depends on the masses of the stars involved and how things go. For example, if we have one type of star is a neutron star and the other star is, say, a red dwarf, the neutron star can actually steal the outer elements of the red giant and actually form a black hole by gaining enough mass to overcome the neutron degeneracy pressure and then form into a black hole. It's a very fascinating process. It's very difficult to show this with Barnes-Hut simulations that I usually use, so I'll probably not make a simulation of that, but I am going to make simulations of other types of star mergers. Another type is where you have one very compact star and another with a more bigger atmosphere. Stars have very large atmospheres in some cases, and the atmosphere can get pulled off by the smaller star and become part of the other star system before the two stars merge into one. When this merger happens, they could again form into a black hole possibly, or they could form into some other kind of object. If it's not enough mass, it could form into a neutron star, or it could form into a white dwarf if the two stars were originally very low mass. So here we have a large star with an atmosphere and a more densely held star. Now, when these two merge, the atmospheric components go on the outside. And in actuality, some of that would actually get pulled into the core immediately. But you get the general idea. We have that this forms into one giant star with a more prominent atmosphere. We can also have it that a star actually steals from a gas cloud. So here we have a small cloud of gas that's getting pulled under the gravitational influence of a star. And in actuality, when these mass components of gas get close enough, this system would just capture it. However, this simulation only models gravitational influences. So you'll have to use your imagination a little bit. I do work with high resolution simulations called fire simulations, which actually do have the dynamical processes where when the gas gets close enough to the star, it merges and becomes part of the star itself, and the star actually gains mass. But these Barnes Hut simulations are just a lot simpler, but they're still nice to see. You can see how this gas cloud has been completely engulfed by the star, and in reality, all these gas points would not be hovering, they would just be emerged. Get ready, because tomorrow we're returning to the moon. That's right, Artemis 1 is launching tomorrow. Now, this mission is a very complex operation. It is unmanned, and nobody's actually going to set foot on the moon, but the ship is going to blast off from Earth and enter a retrograde orbit around the moon and release satellites, which are important tools that will assist us in future missions where we actually set foot on the moon. So this is a first step in reaching what will come to be an age where we actually set foot on the moon more regularly. We need more equipment and satellites to assist in GPS around the moon, just like we have these GPS satellites that assist us with locations and communications around Earth. So, while it's unmanned, this is a very big deal, and it's a very fascinating mission because the orbit that the ship is going to actually enter is a retrograde orbit at a Lagrange point. And if you've studied classical mechanics, you know a Lagrange point is a mathematical solution to the three-body problem. What do I mean by three-body problem? Well, we have three gravitating bodies, the Earth, the Moon, and the much smaller massed spaceship. Now, at this Lagrange point, there's an equilibrium point where the gravitational pull from the Earth and the Moon is equal, and this is a stability point, which is very useful because it's a lot easier to maneuver at this specific location. The calculations are a lot simpler for the crew on Earth that's actually guiding this ship. So that's why they've chosen this location. Now, this mission is going to last about 3 weeks, and then the ship is actually going to return to Earth and splash down. This reason that it's going to actually return to Earth is twofold. Number one, it saves us money because we don't lose a ship and have to worry about maybe it being destroyed. Now, I'm not 100% certain that the ship will be reusable. I think that it is. However, even if it's not, this is an important thing because we need to demonstrate that we can bring people back from the moon once they journey there. So this is an important early run. Now, what's a future mission where we actually set foot on the moon going to look like? Well, probably we'll do something with these retrograde orbits in the future where the ship will enter a retrograde orbit and then bring down a smaller test craft that actually lands on the moon and is controlled by the actual astronauts themselves. So stay tuned because we'll see what happens with future missions. But this is a big deal and it's happening tomorrow, so stay tuned. What is this crazy object behind me? This is Io. It's a moon of Jupiter, and it orbits roughly 420,000 kilometers away. The colors that you see are the result of all these volcanic eruptions. You see, it has over 400 active volcanoes that regularly erupt and litter the surface with sulfur and sulfur dioxide. And the eruptions can go as high as 500 kilometers or 300 miles above the surface. What causes all of these volcanoes to exist is frictional forces within the interior. Plates push up against each other just like they do on Earth, causing volcanoes. But the forces are due to tidal forces between Jupiter and its other moons. A lot of people ask me, which interpretation of quantum mechanics do I think is valid? Let me just summarize a couple of them here really quick. There are many others. So there is the Copenhagen interpretation. That's the one accepted by standard physics. And basically what it says is that a particle could be described as a wave function. The wave function has all of the information about the system, from the possible positions that the particle can occupy, to the possible energies that the particle can have, to the possible momentums that the particle can have. And it can exist in a superposition of these until we make a measurement, at which point one of these possible values is actually measured. But then if we leave the system alone, it goes back into this superposition after a certain unspecified amount of time. Now, this is an incomplete interpretation of quantum mechanics, in my opinion, because the length of time specified for how long it takes the system to go back into the superposition is not explained. It's not explained why, when we make a measurement, one of the possible outcomes is chosen. And by the way, the possibility is random. It's like flipping dice. Hence the term, God doesn't play dice. That's why Einstein didn't like this interpretation of quantum mechanics. However, this interpretation of quantum mechanics perfectly explains the behavior of the atoms and the behavior of the electrons. So as far as making predictions for possible values, I think that the theory is perfect at making predictions. As far as explaining what's actually happening, like physically, why is this occurring? There's no explanation given. So that's why it's an incomplete description. Okay, what about many worlds? Many worlds says all the same things as the Copenhagen interpretation, except it goes one step further, and it says when you make a measurement, one of those possibilities is chosen, but there's nothing special about that choice. So all the other possibilities also get chosen in other universes, and everything splits apart into multiple universes every time a choice is made. I doubt this because it doesn't obey any kind of principle of energy conservation. However, as we've seen, energy conservation isn't as strong as we would have thought in classical physics. It can actually be violated in general relativity as well. However, I'm just ultimately skeptical. My end statement is this. I do think that quantum mechanics is incomplete in its description, and I do believe in the future, perhaps the near future, we will actually have a much better understanding of the physical mechanism that lies behind this wave function just choosing a value. And it might still be that it's random, but I think that we will have an explanation in the future at some point as to what's really happening. The Einstein field equations describe all the incredible effects of gravity as the bending of space and time. But there's a huge problem. While these equations work brilliantly and describe a whole host of incredibly experimentally verified effects such as gravitational lensing, black holes, and even dark energy, these equations, which describe the force of gravity as the bending of space and time by energy, have a huge hole in them. And the problem deals with the uncertainty principle. According to the Heisenberg uncertainty principle, the uncertainty in position times the uncertainty in momentum must always be greater than or equal to h bar over 2. This means that the position of an object is never certain, but that means that the gravitational effects caused by matter and energy bending space and time is fuzzy and not well defined because we can't precisely define where an object is. While common sense would dictate that the object is probably located in the vicinity of this uncertainty range, and the uncertainty range is tiny, to be precise, we need to understand how this interaction of gravitational effect caused by the bending of space and time manifests itself in this quantum mechanical uncertainty regime. This is one of the big problems that needs to be solved in order for us to have a unified theory of physics. This is sort of the quantum gravity problem in essence, because we have this uncertainty in position and momentum, but with an uncertainty in position, we have an uncertainty in gravitational bending. So we need to understand, how does this manifest itself, and how do these two different aspects of nature interplay and relate to one another. All right, let's answer some questions. A viewer asks, why do electrons exist as a probabilistic wave function, but protons and neutrons not? What accounts for this difference? Actually, everything exists as a probabilistic wave function, even you, but there's a reason we can't observe it in larger objects. Even it's harder to observe with protons and neutrons. The equation for the matter wave is behind me. Notice that the momentum is in the denominator. That means the more massive an object is, the smaller that wavelength is. We can actually use electrons as microscopes because we can diffract off of their matter waves. Their matter waves are so large, we can actually use them. However, more massive objects have much larger momentum. And remember, that thing in the top is Planck's constant. So it's really easy to shrink it down. And even our own bodies have a matter wave, but they're too small to observe. The biggest lie you'll hear is that entanglement allows faster than the speed of light communication. That's not true. And there are a good number of videos and sources that point this out, but they usually don't explain why, at least not in an easy to understand way. But here's the simplest explanation for why they cannot communicate faster than the speed of light. Let's say we have two observers, Alice on one side and Bob on the other side. Now, they could be separated by a distance of a light year or a couple hundred feet. It doesn't matter. The point is, let's say Alice measures an entangled pair of a particle, like an electron, and let's say she measures it to have spin 1/2. This entangled electron has a partner, like a positron, that has the opposite spin. So when she measures her spin to have 1/2, Bob must measure his particle to have -1/2. That's in the case that the entangled particles came from a spin 0 particle, like a pi meson, that split apart, because spin has to be conserved. So as soon as she measures the spin of the electron, she finds 1/2 and he finds -1/2. He could do the opposite. He could measure his first, and he might find, for his particular case, that his particle has a spin of -1/2, while she finds then that her spin is 1/2. The point is, the spins always have to equal 0 because the entangled angular momentum, the net angular momentum of the system is 0, and that's conserved. Here's the part that controls whether or not she can do it faster than the speed of light. If she could control her measurement and guarantee that her particle was measured to be -1/2 and control that, then she could decide when to do the measurement, and she could time it, and she could transmit her information faster than the speed of light potentially. But she cannot do that, and he cannot either. If one person makes the measurement first, the other person has no way of knowing that that person made the measurement and that there should be a value associated. If they could control that, then he could know even before he made the measurement what the result was. But since he has no way of talking to Alice when she's separated at some given distance, he has no way of knowing the result of her measurement, and she can't control that result. So she can't say, I will definitely measure the spin to be -1/2 at this time, and I can guarantee that. If she could, then they could communicate faster than the speed of light. All right, enjoy this latest clip from my brand new documentary on dark matter, out now on YouTube. Click the link in my bio and watch the full thing. It's an hour long. I promise you will love it. So what you're looking at here is line of sight views of photons that I would see from gamma ray emission. But how do I actually get these sky maps, which is the galactic view of all the light coming from different angles? I'll show you how I do that right now in simulations. In order to get an accurate picture of what our telescopes observe, I have to orient myself in the center of the galaxy, 8 kiloparsecs away. So I do that here with this line of code. I take a coordinate transformation and I transform into spherical polar coordinates using these lines of code. And then I actually select a distance that I want to orient myself from the center along the x-axis which in this case, this D variable will be 8.3 kiloparsecs. And that positions me at the right location where we're actually located in the Milky Way.